So as yesterday, even today we have a panel. So today the title of the panel that I'm happy to chair is Quantum Technologies. And like just to trigger, so before I will just give short time to the, let's say, panelists to introduce themselves in case you were not here before or you lost any presentation, but then I just put this to trigger a bit the discussion, because this is what we read, and this is what we also hear from companies, investors, and quantum, so capital drives technologies. So the panel is quantum technologies, so we will try to make it fruitful. And if you have any question, just tell me, because I would like an interactive discussion, even curiosities, because you also read these when you go to the Quantum World Congress, or so. Yeah, if you have. So please, just introduce yourself. 1 minute.
Okay. Hello, my name is Anton Trushechkin from the Heinrich Heine University Düsseldorf, formerly from the Russian Academy of Sciences. I do quantum key distribution, security proofs for quantum key distribution for practical devices, quantum networks, theoretical, mathematical stuff, and also theory of open quantum systems.
Hello, I'm Saikat Guha. I'm at the University of Maryland, College Park. My background is in information theory and quantum optics. My interests are in looking at quantum limits of optical communications, imaging, sensing, etc., using tools from estimation, detection, information theory to quantify the gaps between quantum and classical, and then figuring out how to bridge that using novel receiver designs. I'm also interested in quantum communications and networking, repeater architectures, error correction codes, etc. Thank you.
Okay, I'm Christoph Hirche. I'm at the University of Hanover, and I guess I'm working on privacy as one thing, but the main topic I'm working on is really like the mathematical quantities that we use to describe information in, well, both classical and quantum information theory. So divergences, entropies, and basically anything you can do with them, like privacy, hypothesis testing, etc.
Okay, and I'm Andreas Winter. I'm at the University of Cologne, and I would say my main interest is quantum information theory, well, Shannon theory, both classical and quantum. Yeah, like Christoph, I'm more on the mathematical side of things. So, we tend to get excited about, mathematical questions or maybe technical questions around the underpinning theory. I also, like, when you listen to my talk, I'm also interested in sort of foundational questions and the characterization of correlations. And I'm following at least the discussion on the applications of all of this theory in the real world and the emerging technology. But I feel very misplaced here as a big expert. So I'm happy to share my opinions about things, but I probably will be more like a discussion.
So thank you a lot for the introduction of yourself. So quantum is now. So your presentations touched communication, sensing, and computing, privacy. So I would like to know, according to your individual application. So we have also panelists not only from Europe, so even like a broader view, because I'm more familiar, for example, with the Quantum Internet Alliance of Europe, etc. So even in US, for example. So what is your perspective on the sentence "quantum is now" and the, let's say, difficulties and the maturity of the technologies? Even on the theoretical side, let's say, the difficulties that you see to make it now or real in the short term. So start from here.
Should I? Okay. I mean, it's always a bit ambiguous feeling when I see these kind of things, because obviously one thing is we share this kind of sense of okay, we're making progress both in the real world and on the theoretical questions, in the uses and so on. And it's also nice to see the attention that we're getting as a scientific field. But at the same time, words like this, they often come from a different angle. They are kind of hype. And hype is something I don't really like, because it really has some negative impact on the people that eventually we want to convince that maybe they want to use quantum technologies one day. But then if you say, oh, this is now, on the one hand, it seems to say, oh yeah, we've made it. Here's the quantum computer. There are enough groups and peoples and companies that have done that. Okay, now we've proven the quantum advantage and we have a functioning quantum computer and we can do this and this. And it even goes further. It creates patently wrong things. A large part of the public is still convinced, not least due to this hype, that quantum computers will solve everything. Yeah, you just stick in your traveling salesman problem, your combinatorial optimization, it will solve it. There's annealing does it, D-Wave does it. And those are patent lies. We know that's wrong, but we are oftentimes not even anymore able to correct it. And so I always like, as a scientist, I feel like, no, we should probably continue making an effort deflating those things. Because if we don't do it, then somebody like Sabine Hossenfelder does it on her YouTube channel. The recent video about puncturing the quantum hype everything is correct about it. It doesn't change the fact that she's done it before and she's done re-hyping it and de-hyping it. But this is kind of the view from outside. Like we are sort of overselling it, and then somebody has to come and puncture the bubble. And just kind of don't like this. So there's a lot of interesting things going on, but it's sort of drowned out by overhype. So it's kind of my take.
Yeah, I guess I generally agree with Andreas's opinion. Particularly if I now look at our research, I guess a lot of, at least for me, it's like a lot about it is understanding kind of these noise models in quantum computing and so on. And it's often more about proving what we actually cannot do, right? So there's like very intrinsically this motivation of like keeping the hype in check to some extent. But of course there's like this problem of like we are simultaneously benefiting from it. Like for example, in our institute, right, we are getting now funding particularly to advise companies on whether it's a good idea to invest into quantum, or how quantum computers can help their particular applications. And it's somehow sounds a bit hard to imagine like the answer shouldn't just be no for most purposes that we are asked to kind of do, right? So it's like certainly for our field, it has good points that we have this hype kind of, but we have to be careful that it doesn't get out of control, or maybe it already is out of control, and we'll kind of have to make the best out of it with, I don't know, making good research to.
Sorry to interrupt you, just for the privacy point.
Oh.
There is a lot of research on blind computing, for example, or let's say in this context of the hype, the application of blind computing. So, what do you feel? In terms of timeline, in terms of readiness, difficulties.
Well, I guess I give the question maybe later to Saikat about like how close we are like to actually achieving these things, right? But I guess what makes sense is like that we're trying to be ready for when it comes, right? And that is, if you read now in the news that certain, I don't know, messengers or even like encryption schemes, they're going for these post-quantum cryptographic methods and so on, and that's certainly something that's like worthwhile just for the case that it might be coming in a couple of years or something. I let Saikat comment on how close we are. I think you know more about
I can
implementation.
I can comment a little bit. I mean, we'll say that I'm a theorist, but at the same time, my group, I'm very closely connected with experimentalists who I collaborate with, even within my group and outside, so I can comment a little bit on this. Before I talk about blind quantum computing, I put a little bit of a positive light on back. So no, I'm really I 100% agree with what Andreas and Christoph said about the hype. I hate that. Okay, so if you look around us right now across the world, there is some tremendous progress that has been made in quantum technology experimentally across the board. Like you can, it's it was when I was a grad student back, 20 plus years back, it was unimaginable you could go buy a squeeze light source. Right now you can go to ADVR and get a 3 dB, 4 dB squeeze light source with a packaged homodyne detection and bring it to your lab and build systems with it. You can buy single photon sources. People have built quantum memories of various kinds, done multi-qubit gates and trapped ions, generated entanglement across, in the Boston area, Professor Michel Lukin's group has done some very, very nice experiments where they have generated heralded entanglement between silicon vacancies in diamond across a 15-kilometer link in the metro area. So the thing is that all of this progress, if I were to make a catalog of everything that exists right now, it would be amazing to do that, by the way. And then connect that to all these theory ideas, including I'm myself to blame as well. All these crazy ideas on receivers and error correcting codes and these stabilizer projection measurements. The kind of resources we need to get there, we are not there yet. Okay, so now what is happening is there's a funny sort of stretch that is happening at academia. Like if you look at, say, not to pick on somebody specific, but let's take one of, since you were talking about blind quantum computing. Misha's group and I work with them very closely. The student, we did an experiment, it was a series of papers on generating entanglement between a silicon vacancy coupled in a highly coupled cavity, using a weak coherent state reflected off of the cavity to generate entanglement heralded between two silicon vacancies in two dilution fridges. They published that, and the next step was, well, what do you do with it? The next student came along and they said, well, we do a teleported gate with that. So they did a gate teleportation of a full universal set. And then wrote a paper in Nature saying, blind quantum computing over distributed 15-kilometer long quantum. Well, and the paper's introduction would say, if you go deep, say, well, all the primitives you need for blind quantum computation is distributed, being able to do a teleported gate for some universal set, and you have everything you need. But is that a demonstration of blind quantum computing? Well, no, right? I mean, similarly, you would see papers written on, well, entanglement-assisted telescopy demonstrated over a long distance. What you have actually done is a demonstration of a particular 2-qubit gate on both sides of a single bell pair that is established, that on paper are the same gates needed to do a entanglement-assisted estimation of a relative phase between these two qubits. Excellent experiments, but what the press is seeing is as if we are this close to entanglement-assisted telescope. We are absolutely not close. It's still very, very far away. So again, to totally supporting what Andreas said, that we have to keep the hype in check. On the other hand, I'm very excited about the way the technology is progressing, and I think what we should do, I personally really am interested in figuring out small things that can be done already with things that exist right now. I was telling Andreas over the coffee break, Stephanie Weyners, my colleague, she leads the quantum networking effort out of Delft. So Stephanie and I, we are constantly in discussion about what happens in Delft versus our Center for Quantum Networks in the US. So she's organizing a workshop in Spain in May. And it's, I forget the title of the workshop. It's called something like Global Reality Check of Quantum Networking. And the rule there is that the speakers will have, so she invited me to speak there, we'll have these 5-minute talks and no roadmap slides. Like, they only want to know what actually exists right now in your lab across the whole world. So I'm very interested in seeing what comes out of that workshop. But anyway, with that, I'll stop and take any comments.
Okay, thank you. I would like to also to illustrate the hype that we, the community, raise about quantum technologies. So maybe you know that recently a preprint was published that the number of physical qubits required to break RSA 2048 is reduced from several millions to just 1,000. Yes, of course, it's an interesting result. And my friend in Russia, scientist, organizer of science, who calls himself quantum evangelist, published in his blog a title, so breaking RSA 2048 will be possible in 5 years. Why 5 years? And in the text it was written, under the condition, then the number of qubits will double each year. What is the reason for such assumption? And Moore law in quantum computing is not yet known. And even in classical computing, Moore law is doubling not each year, but each year, 1 year and a half. And people from the business world read such titles and think, oh, yes, really soon in 5 years we will have powerful quantum computers which will solve all the problems and break ciphers. So urgently we need to invent something. So yes, and on quite literally these days, these weeks, on my eyes, there was an example of hype created not by journalists who don't understand something well, but by our community, by scientists. So yes, I was surprised about this. But back to the question, what is for me quantum is now? For me, it's I agree. Nevertheless, I agree with this title, Quantum is Now, because yes, it's very exciting what we can do with quantum, with both quantum computers and quantum communications. Yes, if we look at this from the viewpoint of the business world, yes, maybe it's not very clear what kind of applications will be a threat of a quantum computer. Maybe it's post-quantum computer can be a better solution, more obvious solution than quantum cryptography. But nevertheless, for me, quantum world is like science fiction. It's very exciting that we can build our world. Maybe we shall be not so mercantile, not so pragmatical, and simply enjoy what we can build, like quantum repeaters, quantum communication. And then we will see what will happen and what we can do with this practical. So for me, it's and of course an exciting world what we are observing now. And if we tell about future applications, maybe the most exciting application for me in quantum networks will be not communication and security, but yes, precisely what's written here, sensing. So maybe we will be able to do better distributed measurements, distributed clock synchronization to be able to perform new experiments. For example, personally for me, very exciting testing of quantum gravity. There are proposals about experiments to test superposition of space-time, whether it exists or will or maybe it causes collapse of wave function. What will happen? For this, we need to have very precise measurements and very precise time synchronization. And maybe these quantum technologies, quantum networks will help us to do this experiment. And this will contribute to fundamental physics, to quantum gravity, more than the theoretical works of specialists in quantum gravity who develop models, but which are not often not based on real data. And quantum technology can help to do new experiments with to provide new data for this. So yes, I'm very hype is true, but nevertheless I'm very excited about this. That quantum is now. Thank you.
So just to connect to what you said, I had the experience of a master student coming to me and asking a thesis how to break RSA. Immediately for the master thesis. So a real story. I'm not inventing. So just for the hype. So, but we heard that, I mean, noise, error correction, and both in communication and computing are somehow an open challenge. And also in the repeater context, for example, in the long distance. So about these aspects, so the reliability of the communications or the computing, and in the context of short and long distances, for example, if we think about repeaters, what is your opinion when you think about like the real application in technologies, because also, for example, repeaters are not ready today. I mean, so if you have an opinion.
Okay. So about communication, I mean, this it's interesting what Saikat mentioned. This quantum internet workshop. I believe that I'm a bit on a blacklist there, because once I published a joke paper where I was sort of making fun of the quantum internet, and maybe some people didn't really take it with a good humor. But the thing is, it bothers me. I mean, one of the things with the quantum internet is, I mean, we have sort of a clear objective. We want to realize reliable quantum communication, and in practice, what it means, we want to have reliable sources of entanglement so we can teleport stuff. And then the entanglement itself, it could be useful for other things. We know already, okay, once we have it, we can do cryptography, maybe even device-independent cryptography. And so, I mean, from my theory perspective, I think we are still kind of lacking. It's a bit like in quantum computing. We know that there are certain things that are definitely valid, that are not possible without quantum. But just like in quantum algorithms, where there's like since Shor, we had a few advances that showed, okay, other cases where there would be a provable quantum advantage, where we have actually something. In communication, I think we still need more applications of this entanglement. I mean, if it's just, you know, these punctual things here and there, I mean, this is one of the reasons why I got interested in this game theory stuff and in other similar things, because it's an instance of coordination without communication, between coordination of actions. And so that's why I'm particularly proud of this result that I tried to present here, because we actually don't even need entanglement for that. So we can, I mean, it sort of brings it closer to reality if I know anything about reality, because there's a quantum advantage just distributing single quantum states. One could do essentially a classical device could do the communication, and then eventually locally some quantum state is produced. So that's definitely doable nowadays. And so I mean, especially as one who once made fun of the quantum internet, I feel very much dedicated to thinking of more use cases. I mean, theoretical, but also more practical. I mean, thinking about practical. There was another part of the question. I mean, the thing is exactly. I mean, the thing is, we have a lot of progress on the individual device level. Yeah. So I'm very happy that I kicked off with this negative round, so that Saikat could remind us what the immense progress we made on sort of individual devices. In fact, I mean, like in quantum computing, they reached this stage, okay, now these kind of, you know, Google, IBM quantum computers, they are an order of 50 qubits. They can do certain things. I mean, it's not like a full computation with 50 qubits, but you have an immense control. But this 50 is a wall, which is because of error correction. And the same in communication. We are still stuck with kind of a scalable error correction architecture. And of course, that is really the main challenge. I mean, we don't see any reason why it shouldn't be possible to overcome it, but also at the same time, we're still lacking the tools to do it. So the kind of error correction, and even all the way going back to theory. I mean, finding better error correcting codes, or error correcting codes that make the fault tolerance a little bit more efficient, so that we can lower the threshold. All of these are very important things and very exciting questions also in the light of what we can do now. So yeah, I think those are the two things that you mentioned.
Okay. Yeah, I guess I also wanted to comment first on basically following up on what Saikat said. I think it's a very good point that there's a lot of technological progress that's actually continuously made. And I think that also kind of provides us with somewhat of a silver lining in the whole process in some way. Even if like in whatever many years we figure out that quantum computing isn't actually that productive for the economy or whatever, like people think it's now, then at least now at this time when we had all the funding, we learned a lot about how quantum mechanics works and how, like what it does in, I don't know, like how it can influence maybe other fields of science that we don't even know about yet. And otherwise, about current technology, I think I agree with Andreas on this point. It's really like we are seeing this pathway where it could potentially go, and we have like some ideas how it could be used in chemistry or other fields with like optimization algorithms. But we are still there's like this very fundamental questions how we can do scaling and error correction in even just like algorithms, right? If you look at how a lot of effective programming and like implementing algorithms is done nowadays in the classical computing, is like we have the machines and we just try things. We have heuristic algorithms that perform way better than anything we can prove theoretically. So there's a whole range of things that we might be able to do once we actually have these machines, which we can't even judge right now. But it's just the expectation to get like economic value out of these machines at this point in time is probably something that we can't really deliver. And yeah.
Okay, sure. I can maybe first comment on. So your question was, what can we do with quantum communications, right? I mean that, or reliability is a problem. Exactly. Absolutely. You cannot build a repeater if you don't have quantum logic. I keep telling, this is one of the things that people think you just do a Bell measurement and demonstrate entanglement swap. No, you have to have the quantum error correction. You're absolutely right. We are still quite far from repeaters. See, there are two ways to address this question. Like one is, as Andreas was saying, if you have the quantum internet someday, like if you are able to upgrade the internet to provide this new service of quantum communications, high fidelity, reliable, high bandwidth, long distance, what can you do with it? That's a very nice question, and as Andreas said, it will need more answers. There are many things out there right now. For example, you can use entanglement for distributed measurements of correlated phase information for, say, gravitational wave measurements, telescopes. We did a paper on entanglement-assisted telescopes where you can show that you can do, arbitrary quantitative image estimation of sub-Rayleigh objects that are far better than you can with classical correlations alone. But then if you look underneath the hood and say how much entanglement, what fidelity, what kind of memory registers, what kind of quantum logic, what kind of coherence times you need, they're crazy. Like there's no way we are doing them anytime close. But it's useful research. It's very, very important. Right? We are publishing in PRL, whatever. They're good things. I also love these applications of what Andreas was talking about, quantum games. Think of these as, a lot of people call these distributed security, privacy preserving computations, broadly speaking. Like there's auctions, there's symmetric private information retrieval, there's all sorts of game theory techniques. And that could be a huge open up application areas in people who care about privacy. And then distributed computations themselves, like when you have your quantum computers that are distributed over a location, if the information to be computed upon is also distributed, then you would need quantum connections, internet connections that are entangled. Blind quantum computing, you mentioned that. That's often cited as a very important application, but it requires a lot of investigations. Still, in terms of new use cases. The other way to ask this question is what I was saying earlier, what can we do now? Based on what we have? And I feel that's a very interesting research direction that is promising now based on the kinds of things you can do. I mean, we just heard about, what was it, 50 qubit you said what IBM has right now? I mean, there's, I was talking to somebody the other day, one of my students, that, some of these things we were talking about, measurement-based distillation, etc., some primitives that come from network theory-like research, people who have quantum computers, they're typically not thinking about them as use cases to demonstrate, but quantum computers are becoming big enough that we can try out interesting protocols. Entanglement-based sensing, we can try GSZ projective measurements for switching entanglement across multiples. Like lots of cool things you can do right now. Quantum use of quantum resources within a receiver. I mentioned in my talk one use case of super additive capacity, but there's lots of use cases in sensing and where you can use quantum resources locally within the receiver can get better performance. I have a student, she's looking at sending a squeeze light through a spatial mode sorter can generate a spatially entangled state of light that can be used for higher precision beam deflection measurements. It's a very interesting use case of entanglement-assisted sensing, but here the network of sensors are just co-propagating orthogonal spatial modes of light, which are getting different views of the world of when you have a tiny deflection of the beam, and that whole thing mathematically unfurls into an array of Mach-Zehnder interferometers where the phases of those MZIs are all correlated functions of that single beam deflection parameter. So the same mathematics that underlies the distributed telescopes helps you in a single beam deflection measurement by entangling across the spatial modes. So thinking of things you can do with what we have right now is, I think, a very important pursuit that can lead to new ideas.
Okay, thank you. I would like to share one view about quantum networks, quantum communication from practical people. I have experience of working, of collaborating with startups in QKD in Russia and United Arab Emirates, and one our group leader said that usually scientists are interested in quantum communication and quantum cryptography in rate and distance, and he claims, I think it's an interesting opinion. I would like to agree that for practice, both rates and distance may be not so important, because first, why do we need a high rate for quantum key distribution? In order to encrypt messages by one-time pad. But in practice, it's sufficient to encrypt messages by symmetric cryptosystems like AES. When we have relatively short key for long messages, then we don't need so high rates in quantum key distribution. So rate is not so important. Distance, again, in practice, there is an opinion that in practice, trusted repeater is totally fine. So quantum repeater, again, for me, it's very exciting. It's like we live in science fiction with quantum repeaters, with entanglements switching, but if in practice, maybe trusted networks is trusted nodes, to communicate quantumly or to do quantum key distribution over arbitrary large distances is also can be okay. But what is really important for practice, which is often underestimated by researchers, is first cost and second certification. Because the headache of actually in both in Russia and in Emirates with practical quantum key distribution is to get certification from the authorities who maybe are not very much aware of quantum cryptography, are a little more and yes, I have also experience of communicating with them. It's like sometimes we speak on different languages, and how to convince them. They don't not very impressed by mathematical security proofs of QKD, like we, for example. They are interested in some more concrete things. So I would like to message these two things, that for practice, often the important things for practice are underestimated by researchers. So the things important for researchers and for practical people are different. And for practical people, important things are cost and ease of certification. What I wanted else to say about applications of quantum internet. Yes, I would like to join the opinions of my colleagues. So yes, we need to search. So how can we use quantum networks? Yes, as far as I understand, that the maybe most direct application is a kind of metrology, different kinds of metrological tasks, gravitational waves and so on. Then yes, security, of course, and a kind of like in quantum games, a kind of a mean of collaboration or common quantum common randomness. Also, I was not before this conference. I was not aware about identification channels, honestly speaking. So that with double exponential about double exponential acceleration and also quantum entanglement can help here. It's more can be more efficient than classical shared randomness. So now we are, I think, in the stage of exploration. What we can do. As I said, and then we will see which application will be the most useful. And I also would like to stress the optical quantum communication on the very first day, and yesterday was a poster. So, like maybe the same idea as quantum cryptography, but more, how it's called, lower hanging fruit. But also information theoretic security under quite realistic assumptions. Maybe we shall pay more attention to this optical, not quantum, but optical key distribution, which is also can be quantum. Maybe it will be more practical for in the near future and will help to develop further quantum technologies to employ all this quantum infrastructure, which will be used later for maybe true quantum cryptography.
So yeah, time now is time. So I think quantum is not yet now. If there is just one question to shoot to the panelists rapidly. So thanks a lot for this interesting discussion. And